Okay, let's dive right into this explainer and unpack a really foundational concept in software development. We're going to answer one specific, absolutely vital question today. What exactly is forward engineering? I mean, whether you're mapping out a massive enterprise database or just trying to figure out how complex visual models magically translate into raw code, forward engineering is the actual engine driving all that creation. Here is our roadmap for today. We'll start off by defining forward engineering. Then we'll compare it directly to reverse engineering. After that, we'll walk through the actual forward engineering process, look at some real-world applications, and finally wrap things up with something called the round-trip context. Let's just jump right in. Section 1. Defining forward engineering. So, what does this term actually mean in the tech world? At its core, forward engineering represents what we usually think of as the normal development process. It is that standard traditional path of taking abstract requirements and building a tangible working system from scratch. You might actually hear it called a couple of other things like renovation or reclamation, and that makes sense, right? Because you are quite literally reclaiming an abstract idea and renovating it into a concrete reality. You are basically taking a high-level design, maybe a visual model or a complex set of business rules, and translating that into detailed, low-level execution data, like actual source code. Now, I really want to point out the high level of skill required here. Translating high-level business logic straight into a working architecture, yeah, that is no easy feat. Since it's a top-down approach, it is highly prescriptive. You literally have to anticipate what the entire system needs to do before you've written a single line of code. And because you are building entirely from scratch, it demands some serious proficiency. As you might guess, it's also generally a lot more time-consuming and resource-intensive than just tinkering with a system that already exists. Moving on to Section 2, forward versus reverse engineering. Let's compare these two methods. To really wrap our heads around this concept, it helps to see that these two methods have an exact inverse relationship. Look at the real-world examples here. They perfectly hit the nail on the head. Forward engineering is like building a brand new solar panel from a stack of schematic blueprints. You have to know exactly what you're doing to build something that actually functions. Reverse engineering, on the flip side, is like taking apart a musical instrument to study how it makes sound. Forward engineering is all about anticipating the future. You are prescribing a totally new reality. Reverse engineering is reactive. You are adapting to and documenting a reality that is already sitting right in front of you. So it really is a showdown of directions. It's diving down deep into the weeds of execution versus climbing backward to extract the design. Forward engineering means you start with that big picture, the high-level abstraction, and you meticulously carve out the detailed, low-level implementation. Reverse engineering? You start down in the weeds with the code itself, and you work your way backward to figure out what that big picture was actually supposed to be in the first place. All right, Section 3, the forward engineering process. Let's look at the actual procedural flow here. What you are looking at right here is a high-level UML state chart. UML stands for Unified Modeling Language, by the way. This specific diagram basically acts as an abstract blueprint. An automated system, like a code generator called J-code, for example, will look at this and use it to automatically forward engineer fully executable Java code. You can see the top-level states labeled A, B, and G, and all the little transitions between them. To us humans, sure, it just looks like a standard flowchart, but to a forward engineering tool, this is the exact, strict mathematical logic it needs to go write the underlying source code. And honestly, it feels like magic, but it's really not. As you step from those abstract concepts down to actual execution, the system is meticulously, mathematically transforming those visual nodes into real programming objects. When a state splits or merges in the diagram, automated systems are converting those visual cues directly into Java classes and methods, completely automatically. It's pretty wild when you think about it. Let's hit Section 4, real-world applications. How does this actually look in the tools developers are using every day? Well, if you use MySQL Workbench for database management, you might already be doing this without even realizing it. You literally follow this exact 5-step process to forward engineer a visual database model, which is called an ER diagram, into actual runnable SQL code. You just visually draw out your tables and how they relate to each other, and then the software generates the data definition language scripts for you. You can even tick options like drop before create, which just tells the script, hey, delete any old tables on the server before you build my new ones. It completely bridges that gap between drawing a visual database and actually creating it on a live server. That saves developers literally countless hours of mind-numbing manual coding. We also see forward engineering pop up in a few other really crucial areas. Take domain-driven design, or DDD, for example.
System architects might map out a really complex business, say a drone delivery service, and model core functions like shipping or drone management. Then they forward engineer those abstract visual models directly into independent cloud-native microservices. We even see it in education. George Washington University actually uses UML diagrams to help students identify vulnerabilities, teaching them how to forward engineer secure code straight from that visual analysis. Oh, and a quick terminology alert for you. While we are discussing a methodology today, please don't confuse it with the popular tech job title Forward Deployed Engineer, or FTE. That title simply refers to software engineers who work on-site embedded directly with a client to deploy solutions. It has absolutely nothing to do with the actual software methodology of forward engineering that we're talking about right now. Just a quick heads up there.
Finally, Section 5, the round-trip context. Let's look at what happens when this entire software lifecycle comes full circle.
So, when you combine forward engineering with reverse engineering, you get the whole shebang, round-trip engineering. This creates a completely dynamic environment where your raw code and your visual models automatically update each other, instantly. If you go in and change a line of code, boom, the visual UML model updates to reflect it. If you drag a brand new box into your visual model, the code rewrites itself in the background. It is the absolute ultimate synchronization. It basically guarantees that your high-level business vision and your low-level execution are never, ever out of alignment.
So as these software tools get smarter and smarter at writing our code for us, I want you to ask yourself this. Which of these skills do you think you'll need the most to stay ahead in the future of tech? Is it going to be the prescriptive, top-down vision of forward engineering, perfectly mapping out the business models of tomorrow? Or is it the reactive, analytical prowess of reverse engineering, which will absolutely need to untangle the massive mountains of legacy code we are leaving behind? It is a truly fascinating loop to think about. Thanks so much for joining me on this explainer, and keep questioning how the systems all around you are actually built.